All right, so today we are going to talk about how to be a grand pretender or how to not be a great pretender. But um, let's talk about, if you love the trailer that we just played, this is already on Netflix. If you have one account, you should be able to find um, that animation, and this is one of my favorites. But before we start talking about this, right, where are we coming from? So first of all, don't forget that we are living in a world that where every machine is pretty much like a von Neumann machine. By the von Neumann machine, it means that we always have the processor, we always have the memory, and whenever you need to execute a program, everything has to be presented in a memory, and we execute instructions by instruction based on the program counter order, as well as the control flow order of the program. And evaluating performance require instruction count, cycle time, and CPI. But most of the time, we probably won't have the full picture of what a program is about and the detailed information of those. But one thing we could do, and most of the time, what we really want to do is that we want to find out what should we work on, and how can we find out one thing right to do. And turns out the last week we talked about MDOS law. So there are 5 implications that we have learned from the MDOS law is, first of all, each optimization has an upper bound, and use MDOS law, assume the speed up is unlimited, you should be able to find it. And also the second thing is that we should make the common case fast. And the third thing is that optimization is a moving target. So a lot of people, they just keep using their stereotype saying that, oh yeah, if I'm slow, it must be I should get a better GPU, I should get a better CPU. But a lot of cases, is that really the case, right? So using MDOS law repetitively iterated again, that's how we find what to optimize. And the fourth corollary we have is that once we have a machine with a lot of parallelism, and the key to performance gain is no more about just the complexity of the algorithm itself. It's more about by how much degree we can parallelize the program. So one example that we show both in real program demo and mathematical analysis is the Botanic sort on GPUs, which we have been showing that if you have a lot of parallelism, even though you have like just 1,000 parallelism, it's already showing that the Botanic sort is at least twice faster than quick sort or merge sort, even though they have difference in, like Botanic sort is knowing to have a higher algorithm complexity than the other one, right? And so that's why we keep telling you, yeah, it's good to learn algorithm complexity. It's important for a single thread application. However, if you are living in a world of multi-threaded, then complexity is not the only thing that you should care about. And finally, a lot of people might misread my words on that. I didn't say complexity is not important at all. In fact, it is going to be important after we solve the parallel programming problem, right? There are always something that we cannot parallelize it. And in fact, once you have done with the parallelizing problem, the remaining overhead, which is the single thread overhead, is start to come back as the target to optimize, right? Because optimization is a moving target. And that at that point, algorithm complexity becomes important again, right? So that's what our takeaway is. And like as our tradition, we always have a question to ask before the real lecture begins. But right now, I want you to answer my question. But before I answer the question, watch this video. Okay, grab a few people around you. Is this video convincing? Why or why not? Okay, what do you guys think? Is this video convincing or is video not convincing? Are you sold by this product or are you not sold by this product? What do you guys think? Convincing, not convincing? Why or why not? Any thought? Okay, what do you think? Mm. Okay, so looks promising, but some questions, right? What else? What do you think?
It seems like not typical work like flow. Like most people, I don't think have 4 programs per window and 2 monitors.
Mm-hmm.
Some people might, but I don't think most people are using the computer for that.
Okay, so it's not demonstrating a typical use case of a laptop computer. Okay, what else?
They don't specify the
Okay, so they don't tell you what exact detail of the competitor's computer is about, right? So like how big the RAM is, what kind of processor is that, right? What else? Like they didn't tell you who is the competitor, right? What else?
There are no exact timestamps on when the programs started, when they ended.
So when you say the timestamp, elaborate more on that. Because they do have the timer counting down, right? Is that insufficient or?
I think so because it's possible the video was edited and the timers were placed on.
But you know, right now with generative AI, I can also put a clock, right? So you know, it's interesting. I don't know if some of you watch some of the like American TV series. There's one that I like the most, the Newsroom. I don't know if any of you know that. It's a TV series. The script is written by Aaron Sorkin and the same script writer of the Social Network movie, and there is one episode. There was one like a general or something, like a very like a government people, when he decided to take the interview from the reporter. They say, put me on this spot. Like I want to have this at my home, at this couch. And then turns out what he did is that at the time he turned on the TV. So when he did that interview, you can see what's on the TV. So it's something like a timestamp, because what's playing on the TV is not really fakeable using the technology at that moment of time, but it's a good assessment of what's going on at a timestamp, right? Okay, but that's a little bit off the topic. But okay, so all observations you have, they are good, and it's very correlated with what we are going to talk about today. So before today, I believe you guys have done a reading quiz, and the reading quiz, we ask you to read not really a paper, but I would say it's an article, and it's called like The Humor in Computer Science. And sometimes I do feel like, you know, like people typically call us nerds, right? So if we can have more humorous, then the world would probably be better. And, you know, they won't call us nerds. They will probably think that we are more like a stand-up comedy actor or something. Anyway, so there are 12 things that they say how to fold a mess when giving a performance result on parallel computers. And today we are going to talk about several of them, and coherent with that, coherent those with what you see every day, including the video that we have just saw. But before we, so the first topic we are going to talk about today is flops. So how many of you heard the performance metrics called flops? Okay, what is flops? Okay, floating point operations per second. And where did you see we use flops a lot? GPU for what?
Like measuring the
performance of GPUs or gaming consoles, right? So, you know, whenever there is a new gaming console, people like to compare their flops. And if you see like, okay, the latest generation of the Switch, they actually have 3 teraflops. And PS5 Pro has 16 teraflops. And Xbox Series X has 12 teraflops. And people typically would consider the quality of game on PS5 Pro and Xbox Series, they are pretty compatible. But a lot of people would think, okay, the best place to play game is to buy a game console. And in fact, that's where our user experience is, right? But if you really want to use the flop to assess the gaming experience, turns out that you should just like buy an NVIDIA GPU. They will give you the best. But is that really the case? Is that really the case? Right? So there must be something wrong with flops. right? So, and like gaming is not the only place that we use flops a lot. A lot of people, they like to use flops to talk about the performance of AI training, right? So this is a public website from one of the giant company in the world, and they also use flops to say that they have like 20 paid off flops on their products as to show that it's a new class of AI GPU, right? So also in the AI realm, they want to emphasize the importance of flops. But let's take a look. How useful is flops in general? All right, let's take a look. The initial vote shows that we really need some more discussion. So why don't you guys talk to your friends regarding how many of the following statements are correct? All right, let's take a look regarding what you guys think. Okay, after discussion, more of you think there is at least one thing right. Okay, so what's that one thing right? Let's try to dig it out. Is the first one that one thing right? The flops remain the same if we change the data set of the same program. Well, the flop remain unchanged if we change the data set of the same program. Yes or no? Yes, no, yes, no, no. Okay. The second, the flops remain the same if we change the data type to double. No, most of you think it's no. The flops remain the same if we run a different algorithm. No. Running the same program on a hardware with higher flops will lead to better performance. Yes, no, okay. So the reason is 1 because half of you said 1 is yes, half of you said 4 is yes. So 0.5 plus 0.5 is 1, right? Okay, so what is flops indeed? So flops is in general the floating point operation per second, but because of the speed of modern computers, they are really fast. So most of the time, no matter it's GPU or CPU, it's all about teraflops per second level performance. So if we talk about teraflop, right, in computer science, tera typically refers to 10 to the 12. So teraflops per second means that the number of total floating point operations, floating point instruction, divided by the execution time times 10 to the 12. So that gives us the equation here. But in fact, you don't have to memorize it because by definition, that's what it is, right? So saying that today I have such a program, I think it's probably not too difficult for you to know what the program is doing, but how many floating point operations are there if all the array elements, they are floating point numbers? How many floating point operations do we have? 2 times m and k, right? Because you have to run this loop for m and k times, right? And what's inside each iteration actually has 2 floating point operations. One is the element-wise multiplication on floating point, and the other is the accumulation, right? So it's actually 2 times m and k, right? So if today I'm giving you a 2k by 2k matrix to multiply with another 2k by 2k matrix, how many flops do we have in this program? By flops here means the operations is not about per second. How to calculate that? How many that? How many of that? A lot. How much? Okay, so like 2k is 2 to the what? 11, right? So if you have 3 2k, what's that? 33, right? And if you have 1, 2 in each iteration, it's a total of 2 to the 34 operations, right? And divided, so if we want to calculate the flops of this application, right, then, or this particular code, it's pretty much like 2 to the 34 divided by execution time in seconds, and multiply it by 2 to the minus 12, right? So that's how you get this flops number. Okay, so now I'm going to show you a demo with a few different implementations, and let's see the flops of each different different machine configuration. Different runtime on the same hardware. So the computer that I'm using has a Core i7 14th generation processor, and it has 24 cores. And on the same time, we also have an NVIDIA GPU 4070. And now I'm going to run several different configurations in the meantime to see what the performance would look like. And let's see. Okay, so the first one that I am running is a tiled implementation on CPU. So on CPU, like 14th generation of CPU, it has 1.15 gigaflops. And if you have multi-core GPU and if you can fully CPU, if you can fully parallelize it, you can imagine you can probably multiply this by a certain numbers. And based on these numbers, you also know that this implementation is not fully optimized yet. But with that, if I want to run like 2K by 2K matrix multiplication, turns out it would take 15 seconds, right? And a lot of you already know matrix multiplication is the most important, most critical part in machine learning models in general. And if you have turned in programming assignment 1 and you have done the profiling yourself, you know, like the matrix multiplication we spend in backpropagation is actually the most time-consuming one, right? Like around like 1/3 of the time is spending on the matrix multiplication. So everyone wants to make it faster because based on Amdahl's law, that's the critical part. So a lot of people saying that GPU is a better one. So let's look at different GPU approach. So here, I try to run with different data sizes as well. So the first one, I think when I say data type size as 4, it means that it's a floating point. And later on, I'm going to try double as well. So look, so if you just run the same on GPU, it actually costs the throughput is 317 gigaflops, right? Like, look, what's the gigaflops we have for the CPU? It's only 1.15, right? So that's why a lot of people think, well, we should use GPU, right? And actually that's pretty true, right? But if you try different configurations, you will see they have different runtime. So I try to summarize this result that I just ran with a table like this. So first of all, here's our baseline. The tiled most optimized algorithm on CPU, it takes 15 seconds and it's 1.15 gigaflops. And for the tiled version on GPU with data type as floating point, I only need to spend 54 milliseconds. And the gigaflops is 317. And I also tried a standard optimization. So later on in the memory section, we will talk about if you want to optimize matrix multiplication, there is a tiled algorithm that we will teach in the class. And but without using a tiled version, the GPU is still a lot faster than a CPU. However, it does not, it's not as competitive as the tiled version. So you will see that the gigaflops is only 273, right? So what does that tell you? Even with the same data set, right? They are the same size. The algorithm would change. The algorithm would change the flops, right? So it changes as the algorithm changes. Now, let's take a look of 3 and 1, right? So the 3 and 1, you will see they are both tiled version. However, for the 3, we we actually make the data set size 4 times larger by double the dimension on each side of the matrix. And then turns out we got 600 gigaflops, which is a lot better than 2K by 2K, right? And if we grow it to 8K by 8K, then it's close to 700 gigaflops, right? Did you see that? However, if I change the data set to be double numbers instead of floating point numbers, where the data size here is 8 bytes per element, you will see the gigaflops we achieve is only 322, right? And at the same size, it was 600, right? So it changes with different data set size, as well as the data type, as well as the algorithm implementation, right? So flops is not a constant number. Even though you test with the same program, if the data size is different, the flops would change, right? So now, we can also test this on a, let's see, a different application. So now let me do this. Okay, so another machine that I can show you is this RTX 4090, which is a better GPU, as many of you know. And let's take a look of the synthetic result with that RTX 4090 here. So now, so previously you said, well, the GPU I showed there are only like hundreds of gigaflops, right? And didn't I said that We are now in the era of teraflops. So if you take a look of RTX 4090, right, then with 8K, right, we can get like 3.1 teraflops, right? So it seems like for the same stuff, if I run this on RTX 4090, I can get like, this is more like 8 times speed up, right? So can I conclude in general 4090 is 8 times faster than 4070? No, but that's run another program to see if that's generally the case. So our good friend Bitonic Sort is coming back, right? So first of all, I run this on RTX 4070. It takes a total of 0.3 seconds and also 0.2 on the sorting kernel. And now, if I run this on this RTX 4090, this is what I would get. So on RTX 4090, it's also taking about the same time, right? What does that tell you? The flops, they are not transformative, like they are not like transferable to another applications, right? So if we review this question, the flops remain the same if we change the data set of the same program. Is this true based on the demo? The flops remain the same if we change the data type to double. No. The flops remain the same if we run a different algorithm. No. The same program on hardware with higher flops will lead to better performance. Not always, right? So what does that mean? None of this. But even those are the cases where we need a performance matrix to tell us what hardware to use. Right? So why is that? Why is flops so misleading? Why is it so misleading? Why is flops so misleading? What's the main reason it's so misleading?
Measuring like a specific thing, floating point operations, instead of like the general performance.
It's not general enough.
Yeah, or it's
The execution time, it depends on the execution time. Tell me more about it.
I mean, a program does not always depend on this floating point operations, right? It's not just
Okay, so floating point is only part of that. Okay, that's a good argument. But even though it's floating point intensive application, do you think flops is good enough?
flops only measure the computation, right? But you also have memory and other things you have to consider.
But that's a synthetic result, right? But that's a good thing to say, right? Because the floating point operation may not be constant, but that's set it aside, right? Because all the test cases that I mentioned here, they all fit into the GPU memory. So in this demo, you haven't made any issue regarding memory.
No, I mean like caches and stuff.
Yeah, I mean, it's not there yet.
But we use tile, right? That uses cache.
Yeah, but all the tile algorithm, they are already optimized, right? Agree? Okay. So when we talk about performance, can you remind yourself what's the most important metrics we care about? Execution time. What defines execution time? Instruction count. Cycles per instruction. Clock rate, cycle time, right? So let's recap this formula again. This is T flops. So how do I get the execution time on the bottom side? As you guys said, right? It's instruction count times CPI times CT. How do I get the number of floating point operations in a program? the instruction count multiplied by the percentage of floating point operations. So what does that tell you? Is that at the end, flops is only about number of floating point operations divided by CPI and cycle time. And when we talk about performance, three important factors: instruction count, CPI, and cycle time should all be considered. And the problem with flops is that if you go through this iteration, you will figure out that the instruction count is completely ignored. A lot of people misunderstand the factor that they think, oh, I count the number of floating point operations. But look, mathematically, it tells you you are counting on the percentage of mathematical operations, not the exact amount. So it turns out the IC is completely ignored. So what does that mean? If my program gets longer, for example, when you have larger data set, you need to run more iterations. The percentage of your floating point operation, in fact, they won't change. But when you need more iterations, you are making the IC longer, right? It's completely ignored. If I have a compiler optimization, that could reduce the instruction count. Then the IC is still ignored. So this effect will vanish, right? So a lot of people will say, well, I don't feel there is a huge difference between PS5 and Xbox. Remind yourself, who produced Xbox? Microsoft is a software company. They have better compiler team. In fact, they have the best compiler team over the world. So they could make Xbox with lower cost, with competitive performance, right? And that part you cannot see from the flops, right? And like some people would say, well, in the good old days, people would say, I'm using a RISC processor with higher flops, right? Reduced instruction set architecture. But the cost of reduced instruction set architecture like ARM versus x86 is that you would suffer from higher instruction count. So the instruction count of ARM programs are generally more than x86. And they all say that, well, ARM processor, they have better flops than x86, but they didn't tell you is that we need more instructions to perform a single floating point operation. And that effect is completely ignored, right? So, in fact, flops is the best way to cheat on performance, right? So, because IC is gone, right? And if you review the reason why, as we said, when you expand the data set, you get more instructions, and this is ignored now. If you change the data type to double, the CPI changed. However, the instruction count may also change, right? The flops does not. If you keep using the same flops without referring how you deliver these flops on the data type, it's not going to be representative. And in fact, the latest generation of NVIDIA hardware, they told you, if you switch your data type to double, it's only going to give you 1/8 of the performance of floating point operations, right? So this is a bad news for scientific computing because in a lot of cases, we definitely need double, right? And remain the same if we use a different algorithm because different algorithm, they would deliver different instruction count. And also, right, if the program is floating point intensive, yeah, flops does make a lot of sense. However, a lot of programs, they are not floating point intensive. For example, like the sorting program that I show you, it's more about comparison. Those are not floating point based, right? Then it becomes meaningless to compare the performance using the flops, right? So it turns out flops is very difficult to use. So, and originally, NVIDIA is probably the most advocator of using flops to advertise their performance. But later on, as many of you know, that because for AI training or inferencing, well, especially for inferencing, we can tolerate inaccuracy. So most of the time right now, we don't use floating point for inference for performance perspective. In fact, a lot of people, they are doing this integer inferencing, and from integer 32 to integer 16 and now to integer 8. Recently, I see people talking about integer 4. A long time ago, people have been talking about binary neural network, which is only 1 bit inferencing, but the accuracy is staying at somewhere like 60 to 70% of the accuracy, which is probably not as good as random guessing. So, but let's say like nowadays, a lot of AI applications, they are not floating point based. So if you use flops, that doesn't make sense. So in fact, they are using ops, right? Like they are using ops, like operations per second to represent, or say like AI ops to represent the performance. But does this solve the problem? Does that solve the problem? That's not really solving the problem, but we will talk about that a little bit later. But let's talk about flops first, right? So if you map flops to this interesting article, you will find it matches 4 of the criteria here, right? Because quote only 32-bit performance result, not on 64-bit. That's what NVIDIA have been doing for a lot, right? They only tell you the peak performance without telling you what data type can you survive with that floating point operation. So if today I'm doing scientific computing, I think I should buy like a B200. But considering it's only 1 of the 8th of the performance in the flops they advertise, I shouldn't do it, right? So the second thing, present performance figures as an inner kernel, represent these figures as the performance of the entire application. Flops also focus is also some sort of that, because you can only see the performance of a floating point intensive part, ignoring the fact that maybe in your application there aren't that many, the time you spend on floating point operations is not as significant. The assembly code, I don't think this experiment shows that, but for the fourth one, scaling up the problem size with number of processors, but omit any mention in that fact, right? When NVIDIA tells you their flops, did they ever tell you under what situation we tested that? They didn't tell you, right? And when they measure those, everyone measure those with the best ever flop they can achieve on their hardware. But they don't tell you how difficult was it to make that happen, right? So and typically, if you want to sustain that high flops, you have to scale up the problem. And nobody ever mentioned it. So that's why we see when the data set size are small, we are far away from that advertised flops. And at a time when the paper was written, it was the era of M-flops, megaflops. Surprisingly, right now we are not even in gigaflops, but teraflops. So this is also a good article for you to see how we advanced the technology within the past 30 years. We are like 2 orders of magnitude. And as we said, right, our flops change as algorithm changes. So a lot of people, they don't tell you like what kind of implementation we are using. And in fact, a lot of people, they try to steal some wisdom here. Is like they try to use an implementation with fewer operations to achieve better results. All right. So this is actually so this evaluation we have back to flops. It actually fulfills 4 things that this paper has said. And like 30 years have been passed, you will be surprised people are still doing the same thing. Right? Okay. So the first thing is that if we want to be an honest engineer, or if we don't want to be an honest engineer, right, you should not use flops, or you should use flops. Now, another case study we want to talk about is AI inferencing, right? So AI, a lot of people, when they talk about AI, in fact, in many cases, we were talking about like AI in those classes, we teach you how to train. But in fact, most of the time, 85% of the data center AI workloads is about inferencing. So the majority of the cost is actually spent in inferencing. So let's talk about what's in inferencing. So the basic idea of inferencing is that I take an input and I try to predict what that input is based on the model that I train. So for example, the most common use case is that the image recognition, and you will probably use like a lot of fancy operators like convolution plus ReLU and do a min-max pooling and another layer of convolution, ReLU, and min-max pooling. So this is like a multi-layer convolutional neural network. And the purpose of doing this is that we want to extract as many features as possible. And theoretically, the reason why we do this is that this would help us to sharpen some of the feature points in your image after the convolution. Because if you took the original version of the image processing or computer vision classes, even without AI, we have to do a lot of like convolution with kernels to sharpen the border of your image. And once you have done that, you take a fully connect operation, which is basically matches vector multiplication, to see which category is the most likely one. And for example, if you think this is a bear, a lot of people don't agree. Maybe they think it's a dog or tiger, whatever. But for this particular model, it says it's bear, then we would predict it's a bear. So this later stage called fully connected is actually help us to classify what it is. And the whole thing, this whole process, feature extraction plus classification, is AI inferencing. So, as we said, NVIDIA tried to tell you, they start to recognize that a lot of people like us, we know floating point operations per second is not meaningful anymore, right? So they try to use other things to tell you we have a better performance in terms of AI. So a very, very popular metrics nowadays called inference per second, meaning how many inferences that we can do for a period of time. Is this a good metric? All right. Okay, I love this figure because it means that we need to discuss. Why don't you guys talk about with each other? Grab a few people around you to talk about that. All right. So after the discussion, okay, still a very diverse answer. So CDE, they are both popular. So can IPS change if the application changes the ML model? Give me an example.
When you're selecting your features, if you have like multiple times,
Mm-hmm.
you can just add it.
You can just add, right? So, but in real life experience, like a service that you use with like every day, what do you feel? Do you have any like? Okay, I use ChatGPT every day. I use like, okay, so it's hard to believe that, right? Like this is from a scientific professor, but you know, like I do want to like see what my fortune looked like today using those tarot cards, and it's too expensive to pay a psychic teller regarding that, so I just use ChatGPT. It used to be ChatGPT 3.5, and it was already slow, but recently, as many of you know, they upgraded to a different version of ChatGPT. How do you guys feel? Faster, slower? Slower, right? But what that meant to you is that I'm asking the same question. It's getting slower if I switch from 3.5 to 4, right? So IPS can definitely change if the application changed the ML model used. If the IPS can be worse, if we add more features to improve the quality of the answer. Yes, again, right? So sometimes I didn't change the model, but if I increase the input that I fit into the model to give me more insightful result, then that would change the time it takes to inference, right? So how about the third? If I use a hardware with higher flops, that will improve the performance of IPS.
Yes,
It can? Well, it really depends, right? So this question, I would say it depends.
Says it can. If it does, it would be kind of different.
Okay, does. Okay. Okay, but it really depends on what kind of models you are running, right? So how about the fourth? If I have a system that answers questions 20 times slower, but can answer 20 more questions in parallel, is the IPS the same? Right? Yes, right? So you know, all sorts of things tells you IPS is not a good matrix. It's not a good matrix regarding it ignores a lot of fact, right? So if you pay attention to that, again, it also ignores the instruction count in general, right? So you cannot miss any factor in a performance equation. And like, in fact, if you want to ask like the questions, right, you will figure out that, like they don't care about the quality at all, right? One of them can say, I don't know. The other say, I know who is that, but maybe give you the wrong answer, right? So, so again, the problem with IPS is that similar to some of you pointed out in that particular video that we watched in the very beginning, they don't specify under what condition we measured that, right? They don't tell you exactly what models are they doing, what data sets am I running, what kind of quality of results that I'm delivering, right? So it turns out we need something called a benchmark, which pretty much means a standardized suite of workloads or applications, or they also specify the inputs that you have to evaluate to claim you have better performance than others, right? So like in the era of AI, like there is one specifically popular called MLPerf that define a set of like workloads that you evaluate to claim that it's a better AI system, right? So, but prior to that, like in general purpose computing, like there is also a standard performance evaluation corporation called SPEC. They published like SPEC 2017, this kind of workloads for general purpose computing. So most of the time, if you really want to, and when we design those benchmark application, right? Like some of you said, I don't care about that video you played because that's not what my typical usage of computer. So when you define this benchmark suite, typically they should cover as broad application, as a wide spectrum of application, as representative application as possible in each of the benchmark suite for their specific domain. So by looking at those, it will give us a better idea. I can trust the performance result in their end-to-end latency. Or at least if you want to take a look of the throughput, you would know under what situation they generate this kind of throughputs. Right? So that's the meaning why we need benchmark applications. Right? So specifically, in a lot of cases, and in a lot of like AI papers that we have reviewed, we have seen is that people compare their C code with other people's PyTorch implementation, saying that we get performance gain, right? So, and the reason why we want benchmark is because we want to prevent a case where the quality get changed. We want to avoid a case where the application is not highly optimized, right? And also, like, yeah, sometimes the model changes, right? And people just give you the result using a simpler model with lower quality. That's also a fraud, right? A lot of companies did that. Like 20 years ago, NVIDIA did that as well. When they are advertising their frame per second on the game, they lower the quality because, you know, a lot of you said I can tell 120 hertz refresh rate. Liars. Most of us can't. And NVIDIA played that trick. They just duplicate the previous frame they generated and claim that we can get 120. I deliver 120. It's just the same frame as you see previously, right? And you were not aware of it, right? So a lot of things that those metrics won't tell you, right? So without mentioning the specific conditions or changing more than one factors in the evaluation, the performance result is meaningless, right? So when, in fact, this is true for all scientific experiments. A lot of cases when people measure their result, they change many things at once. It makes it so difficult to judge who really plays the deal, right? So for that Q company video that you guys watched, it never mentioned how much memory is installed on that machine. They didn't mention what kind of GPU was using on that machine, right? They didn't tell you what generation of competitive products are we comparing against, right? Without those information, I highly doubt they run the same workloads on a computer for them with rich memory capacity, with solid state drive versus the other one maybe using a hard disk drive. You never know. Maybe they do. Maybe they didn't. They just didn't mention that, right? If they change so many things at once, are they convincing, right? Okay. So why do we always care about the end-to-end latency? All right, let's take a look. Okay, so I love this figure because it means that we need discussion with others. So why don't you guys talk with each other regarding what this question is? Like, what do you guys think about this question? All right, after discussion, okay. Are you sure you voted again? I feel like everybody is insisting regarding what they think. Okay, so offloading the main computation kernel where the baseline spend most time from the CPU to another computer will improve the end-to-end latency. No? Yes? No? Okay. If we place a file on a disk with higher bandwidth, we will spend less time in file access. Yes? No? A computing device with higher parallelism can potentially deliver higher flops even though each parallel instance is slower. Okay? For real-time applications, we should prefer computing instances that deliver more results per second. Okay, so let's see, right? So let's take a look of the demo that I prepared. So a lot of people, sometimes they question us, why are you guys so keen to latency? Right? In fact, it's kind of interesting. In a lot of commercials, they never told you the exact end-to-end latency, right? If you buy a hard disk drive or a storage device, they tell you the IO operations per second, IOPS. And everybody is talking about IOPS. And in AI, people talk about like inference per second all the time, right? Like in game, frame per second, right? Or flops, right? Nobody ever talk about like how the end-to-end latency. Why, right? So let's see why they don't want to tell you about this, right? So first of all, let me show this example. So right now, I'm running matrix multiplication with a small data size, which is 16. And in fact, in a lot of cases, we only do things on small data sets, right? It's not always the case that we are going to run on large data sets. So first of all, right, if I want to run this small instance, it takes, it gives me the throughput of 0.07 gigaflops, and it takes 0.11 milliseconds on the GPU. And let's run it again with, what if I just run them all at once? Run O below. Okay, save my time. So if you take a look of, oops, let me rerun them. Rerun, run, O up below. Okay, so, very strange. Sure. Okay. Oh, really? Okay. This number is very strange. Okay, that's probably look at the first one is very strange, right? But let's look at the case of 32 and 64, right? One thing you will see is that there's not a huge difference in their latency, right? But if you look at flops, it's very significantly different, right? So on small cases, especially like for each user, right? For example, for ChatGPT, to be honest, everyone is selfish. I don't care how fast ChatGPT give other the like psychic teller result, but I want to know how my taro look like today, immediately, right? So most of the time when we interact with servers, we care about the latency of a small instance, right? And if you pay attention to that, right, no matter how big, how small, it's slow, right? It's as slow, it's the same time, right? It's 1 millisecond, right? But now, if I run this on a CPU, look, how fast is that? Right? On GPU, 1 millisecond at least. On CPU, how fast? Less than 1 millisecond. Right? Why we still need CPU? Because in general, here's a trick. CPU give you a shorter latency because the frequency is higher, the hardware is operating more efficiently for arithmetic operations. So if you have small instance, CPU is going to be more efficient, right? The trick of GPU is they are able to accommodate many tasks in parallel. So this evidence tells you GPU is indeed a case where each instance in the algorithm, we make it slower. However, with that, we are able to accommodate more instances all at the same time. So what does that mean? Is GPU give you better throughput, but in terms of end-to-end latency, it's not always true, right? So if you have that in mind and review this question, the main computation kernel to a device with higher flops will improve the end-to-end latency. Is that always true? That's not a well, right? Not always well, right? So the third one, a computing device with higher parallelism can potentially deliver higher flops even though each parallel instance is slower. Is that true? That's a yes, right? Right? So the first one is wrong, the third one is true. So the same philosophy for disks, right? A lot of people think data centers, they must use high-speed solid-state drive to give me the file access performance. But I want to tell you the truth because if you review my CV, prior to 2019, I work a lot on smart storage, intelligent solid-state drives. But after my visit to Google one day, I totally switched my direction and work on TPUs. But there's a reason for that. Because they told me we are never going to use solid-state drives in data centers. because they are too expensive. But what can we get, right? So if you have a RAID, which you can parallelize the access to multiple disks, your aggregated bandwidth is as competitive as a solid-state drive, right? So you can have sufficient amount of bandwidth, the same bandwidth if you build a RAID with conventional hard disk drive. However, and also the cost is going to be lower if you want to give the same capacity. However, what would that sacrifice is that? Thinking about that, hard disk drive, they are magnetic devices. So it always takes time for them to rotate the disk to the right place where your data is. So that access time is going to be longer. However, in their use cases, for example, what's the largest business of Google except for search? YouTube. Okay, how much time can you wait for a YouTube video to start? And what they do? When you are waiting, we play ads. So they can actually make money while you are waiting, right? So actually they want you to wait as long as possible. So it doesn't matter if you have short latency, but we do want that bandwidth to give you that frame rate you want, right? So that's an example. Like a lot of people would misunderstand in data centers, there are always like high speed solid state drives. And a lot of people, they do research based on that assumption, but in fact, they are never going to let it happen. Unless you can make flash third chip. But that's not in a foreseeable future, right? Okay, so the second is also wrong. Higher bandwidth doesn't mean you are going to have shorter access time of a single file. For real-time applications, a lot of people think if I want to deliver high frame rate, I should use devices with, or say like if I want to have like, if I want to make a fast decision, I should prefer device with more results per second. But from the example that we have shown you, right? If I want to make a decision with a small instance with short period of time, maybe CPU is a better option, right? So considering all of this, okay. And another thing, a lot of people might question why GPU, if you compare the latency between GPU and CPU, there's always that minimum 1 millisecond latency over there, right? Because if you look at the current volume model, the original volume model only have processor, memory, and storage. And everything beyond these three things, they are considered as peripherals. So in the current model, whenever you want to talk to a peripheral device, everyone has to go through this memory abstraction and move data from that memory to their device. So it turns out what happened is that you always have to suffer from some sort of overhead. So let's see, what am I trying to say in this demo? Okay, so in this demo, right, one thing that you can see, if you could remind yourself with this demo, one thing that I didn't say is that when we apply the GPU kernel, there is like this 1 millisecond, 1 second delay in moving data, right? Previously, we didn't mention that, right? Because I intended to talk about that here. When you use GPU, it's not a free lunch. You have to pay the overhead of moving data from the main memory to the GPU. And if you have a small instance, it's actually pretty significant. It's actually pretty significant, right? Like if I have a GPU kernel that's really short, like the matrix multiplication, as you can see, it only takes like less than 0.01 millisecond on the CPU, right? Then other overheads like GPU to host or host to GPU, movement is going to take over, right? So one thing missing in the original format of MDOS law is that it assumed parallelization has no overhead. It assumed optimization has no overhead. However, there's no free lunch. So it turns out when you evaluate MDOS in modern computers, you should consider a factor called scaling factor of the slowdown of the rest parts. And there's not really a formula regarding how to calculate the slowdown because based on what you want to do, that may be different. But typically, for example, if it's data exchange that's linear to the amount of data that you are moving. But what does that mean is that that blue part in this chart is not unchanging. And a lot of us were thinking about if the majority of the program, so for example, like if I say matrix multiplication is 90% of time, I think I should be good to receive speed up if I move to a higher flops device. However, let's do this math, right? If I have a program spend 90% in A, 10% in B, assume an optimization that we can accelerate the A part by 9 times, but hurt B by 10 times. End up, if you do the math, you are getting slowed down. You are getting slowed down, right? So I move a computation kernel to a higher flop device may actually lead to slowdown if the slowdown of the rest part is too significant, right? So here's the sixth corollary of MDOS law is that when you optimize something, don't hurt the non-common part too much, right? So don't hurt the non-common case too much. That's an additional advice from the revised format of MDOS law. So it also tells you why we cannot just ping the performance on a single kernel, because if we just look at a single kernel, even though matrix multiplication is the main thing, God knows if this optimization is going to give you a huge overhead on the rest part. A lot of people saying that it doesn't matter if I hurt like 90%, only 10% of the time. But it's actually not true, right? And I don't want to say this in general too much, generalize this too much, but isn't that an issue in our world, right? We focus on optimize a lot of, like the majority of people who has the right to vote. But they're careless about people, minority people, is actually going to hurt the goodness of the whole world, right? So that's why most of the time we care about everyone. We care about diversity, we care about equity, a lot of things. Okay, but you know, okay. So, but that's that. Don't follow me regarding this. But in general, right? That's why we care about all of those. And but what I want to tell you about in this lecture is that we care about latency because that's the most representative case. Bandwidth is important, but very misleading. So as a computer engineer, you have to wisely choose the right metrics to use. And end-to-end latency is still the most faithful way to evaluate your performance. Before you leave the classroom, a few things I want to let you know. First of all, assignment 1 due this Thursday, and make sure that you submit to right place in a grade scope. Last time, although we did mention this programming assignment, a lot of people some people sent me that later saying that, hey, the autograder crashes, and then I checked, you didn't make any submission. Oh, I submitted the wrong item. Okay, what can I say, right? So I already have the upcoming assignments ready, but now this time I don't put it up because I don't want people to give me that complaint. But it also means that those things are sacrificing your opportunity to start working on an assignment earlier, right? So try to not making the wrong submission. Reading quiz always due. There's always a reading quiz due. I try to make it on every Tuesday, so you have a better idea. If it's Tuesday, something is due. And for Prairie Learn, a lot of people think I can just turn off my computer or I can just move around. And we did mention that you should not consider that to be the case, because once you switch the IP address, once you reopen the browser, it's considered as closed. You cannot redo it again. And a lot of people, they try to send us email late yesterday in the evening. And you're lucky if I saw it, but what if I didn't see it, right? So we would like to help you, but also don't give us troubles, right? And check our website for all the up-to-date links. Grayscope, Discord is the resource to use. And we do have every lecture recorded. Other than that, enjoy the rest of your day. I will see you on Thursday.